SRv6 and network slicing are popular technologies in the IP field. If they are combined, how would we perform configuration? Given that SRv6 supports two modes, namely SRv6BE and SRv6TE policy, let's use EVPN L3VPNv4 services as an example to describe how to configure network slicing in SRv6TE policy scenarios. Network slicing enables us to create multiple logical network slices on top of a shared network infrastructure, with each slice serving a specific type of service or industry. Without network slicing, all services are carried on the same physical network and are likely to affect each other. Although paths can be planned through SRv6TE policy, it is not possible to avoid services impacting each other. In SRv6TE policy scenarios, configuring network slicing ensures that services are separately carried on dedicated logical networks. This eliminates the risk that services affect each other and further guarantees high-value services. PE1, the P, and PE2 all belong to AS100. A bidirectional SRv6TE policy needs to be established between PE1 and PE2 to carry EVPN L3VPNv4 services. In addition, to isolate services, network slices need to be created between PE1 and PE2 so that SRv6TE policy services can run on these slices. We've described the configurations involved in EVPN L3VPNv4 over SRv6TE policy scenarios in another course. You can find that course by visiting the URL shown on the screen. This course mainly focuses on network slicing-related configurations. First, let's look at the configuration roadmap and service logic of EVPN L3VPNv4 over SRv6TE policy network slicing. In terms of the configuration roadmap, EVPN L3VPNv4 over SRv6TE policy network slicing scenarios require two more steps than EVPN L3VPNv4 over SRv6TE policy scenarios. We'll describe these steps later. In terms of the service logic, slice IDs are used to bridge the control and forwarding planes. In network slicing scenarios, we need to configure colors for routes to identify service intents. During data encapsulation, the ingress encapsulates both the SRv6 header and the hop-by-hop options header, which is called HBH for short. During data forwarding, a node searches for the outbound interface according to the destination address in the SRv6 header. Next, the node selects the network slice interface with the same slice ID as that in the HBH from the network slice interface group corresponding to the outbound interface. Network slice instances can be created on demand. They are identified using slice IDs. How many network slice instances we need to create depends on service requirements. After creating such instances, you can add descriptions to facilitate maintenance. Next, we need to specify a base interface and create a network slice interface. Base and network slice interfaces can be constructed on the same main interface, or FlexE interfaces in the same group. A base interface has an address prefix configured for route calculation. It can also be used as a network slice interface. In addition to enabling IPv6, we need to configure an IPv6 address for the base interface. We won't discuss related configurations in this course. A network slice interface does not have any address prefix configured, and only the network slice to which the interface belongs needs to be specified. After a base interface is specified for network slicing, traffic diverted to this interface is forwarded through the corresponding network slice interface based on the network slicing requirements. There are mainly two types of network slice interfaces: Flex-E interfaces and channelized sub-interfaces. This example uses Flex-E interfaces. For details about how to create a Flex-E interface, you can visit the URL shown on the screen. The configuration procedure is as follows. First, run the network slice 10 data plane command on a base interface to specify a slice ID for it. If the data plane parameter is configured, the interface can also function as a network slice interface to forward data. Second, create a Flex-E interface. In network slicing scenarios, we also need to run the IPv6 enable command on the Flex-E interface to enable IPv6, and then run the IPv6 address autolink local command to enable the automatic generation of a link local address for the interface. If we don't run these commands, the IPv6 status of the interface will remain down, and the IPv6 traffic cannot be forwarded. Third, run the basic slice 10 command to associate the Flex-E interface with the base interface. The value of slice ID here must be the same as the slice ID of the base interface. Multiple network slice interfaces that belong to the same base interface form a network slice interface group. When forwarding an SRv6 packet, a device searches the network slice interface group corresponding to the outbound interface for the network slice interface that has the same slice ID as that in the HBH. Finally, run the network slice 20 data plane command to specify a slice ID for the Flex-E interface. This allows the interface to be allocated to the corresponding network slice. Moving on, let's see how to associate an SRv6 TE policy with a network slice. Only one step is involved. That is, run the network slice 20 data plane command in the candidate path view of the SRv6 TE policy to specify a slice ID. In this way, the SRv6 TE policy is associated with the corresponding network slice based on the slice ID. If there are multiple candidate paths, you can configure different slice IDs. Finally, let's look at data forwarding. In EVPN Layer 3 VPNv4 over SRv6 TE policy network slicing scenarios, the ingress also encapsulates an HBH, which carries a slice ID. During forwarding, each node selects a network slice interface with the same slice ID as that in the HBH. The interface is selected from the network slice interface group corresponding to the outbound interface. In this way, EVPN Layer 3 VPNv4 services can be carried on the dedicated slice network.